You exist because of a planet you have never visited. Not metaphorically, not philosophically, physically. The chain of events that produced life on Earth, that allowed it to survive long enough to become complex, that permitted the Cambrian explosion and the dinosaurs and the mammals and eventually you, that chain includes, as a necessary condition, the presence of a specific gas giant in a specific orbit at a specific mass. Remove Jupiter. Not hypothetically remove it, physically remove it, relocate it, reduce its mass below a certain threshold. The solar system that results is one in which Earth is bombarded by impactors at a rate that makes the sustained development of complex life statistically unlikely. The oceans would be reset by large impacts repeatedly. The geological stability that allowed life to evolve from single cells to multicellular organisms over billions of years would be interrupted again and again by events comparable to or exceeding the Chicxulub impact that ended the dinosaurs. Jupiter's gravity has deflected hundreds of potential impactors away from the inner solar system. It has acted, for 4.5 billion years, as an imperfect but real shield, its immense gravitational field catching, redirecting, and ejecting objects that would otherwise have intersected Earth's orbit. You are here because Jupiter was there. But here's the thing that makes this story genuinely disturbing, rather than merely reassuring. Jupiter has also redirected objects toward Earth. The same gravitational field that deflects impactors can, under different orbital geometries, accelerate them inward. Long-period comets from the outer solar system, objects that would have remained in the Oort cloud or the Kuiper belt indefinitely, have been perturbed by Jupiter's gravity into orbits that cross Earth's path. The impactor that killed the dinosaurs 66 million years ago may be one of them. Jupiter is simultaneously the reason complex life was possible on Earth and a potential contributor to the most catastrophic extinction event in the last 250 million years. Protector and threat, shield and weapon. The planet without which you would not exist, and the planet that has repeatedly attempted to end what it helped create. In this video, we are going to go through exactly how Jupiter shapes the inner solar system, what the orbital dynamics actually say about its protective and destructive roles, and what the current state of Jupiter's orbit tells us about the long-term stability of the solar system. There is something in the fifth section of this video that most people find the most disturbing. Not the impact history, not the dinosaur extinction. A simulation result from 2009 that showed what happens to Earth when you run the solar system's orbital dynamics forward by 5 billion years, and found that in approximately 1% of simulations, Mercury's orbit destabilizes in a way that produces a collision with Earth or Mars. A 1% chance that the inner solar system destroys itself from the inside, not from an external impactor, from its own orbital mechanics. And Jupiter's gravity is part of the reason. Stay with me. Before we go further, the Shoemaker-Levy 9 comet impacted Jupiter in 1994, 21 fragments. The largest impact scar was bigger than Earth. If that comet had reached Earth instead of Jupiter, the impact would have been one of the most catastrophic events in the history of the solar system. Drop a comment if you remember watching it happen. It was broadcast live. Before we can understand what Jupiter does to the solar system, you need to understand what Jupiter is. Not in the textbook sense. Not the fifth planet, 778 million kilometers from the sun, largest planet in the solar system. In the physical sense, what it actually is as a gravitational object. Jupiter contains more mass than all other planets in the solar system combined. Not slightly more, approximately 2.5 times more. If you took every planet, Mercury, Venus, Earth, Mars, Saturn, Uranus, Neptune, and merged them into a single object, the result would have less than half Jupiter's mass. Jupiter's mass is approximately 318 times Earth's mass. Its volume is approximately 1,321 times Earth's volume. Its equatorial diameter is approximately 143,000 kilometers, more than 11 times Earth's diameter. These numbers are familiar in the way that all large astronomical numbers are familiar: intellectually acknowledged, emotionally inert. Let's try to make them physical. Jupiter's Great Red Spot, the storm system that has persisted for at least 350 years and possibly much longer, has a diameter of approximately 16,000 kilometers. Earth's diameter is approximately 12,700 kilometers. The storm on Jupiter is larger than the entire planet you live on. It has been rotating continuously at wind speeds of up to 680 kilometers per hour since before the invention of the telescope. Jupiter's magnetic field is approximately 20,000 times stronger than Earth's. Its magnetosphere, the region of space dominated by its magnetic field, extends approximately 7 million kilometers toward the Sun and approximately 700 million kilometers in the opposite direction, reaching nearly to Saturn's orbit. If Jupiter's magnetosphere were visible, it would appear several times larger than the full moon in Earth's sky. Jupiter radiates more energy than it receives from the Sun. It generates heat internally from the slow gravitational contraction of its interior and from the differentiation of its interior as denser materials sink toward the core. Jupiter is, in a very limited sense, a failed star, an object that did not accumulate quite enough mass during its formation to ignite hydrogen fusion in its core. The threshold for hydrogen fusion is approximately 80 Jupiter masses. Jupiter has one. It needed to be 80 times more massive to become a star. It missed by a factor of 80. But even without fusion, Jupiter's mass is sufficient to dominate the gravitational dynamics of the solar system in a way that no other planet can. Its gravitational influence extends throughout the inner solar system. Objects in the asteroid belt between Mars and Jupiter are continuously perturbed by Jupiter's gravity. Their orbits shifted, their trajectories altered, some of them accelerated into the inner solar system, and some of them ejected outward. Jupiter does not sit passively in its orbit. It actively shapes the orbital environment of every other object in the solar system, and it has been doing this for 4.5 billion years. Jupiter's mass of approximately 1.898 times 10 to the 27th kilograms was first accurately determined through observations of its four large moons, Io, Europa, Ganymede, and Callisto, discovered by Galileo in 1610. The orbital periods and distances of these moons, combined with Kepler's third law, provide a direct measurement of Jupiter's gravitational parameter and hence its mass. Modern measurements from spacecraft trajectories, particularly the Juno mission, which has been in Jupiter orbit since 2016, have refined Jupiter's mass and gravitational field structure to extraordinary precision. The Kirkwood gaps are the most visible evidence of Jupiter's gravitational influence on the asteroid belt. The asteroid belt is not the uniform distribution of rocks that science fiction sometimes portrays. It has structure, regions of higher and lower density separated by gaps. These gaps occur at orbital periods that are simple fractions of Jupiter's orbital period: 1/2, 1/3, 2/5, and so on. An asteroid in a Kirkwood gap would complete exactly 2 orbits for every 1 Jupiter orbit, or 3 orbits for every 1, or some other simple ratio. These simple ratios are called orbital resonances, and they are gravitationally unstable. An asteroid in orbital resonance with Jupiter receives a gravitational kick from Jupiter at the same point in its orbit every orbit. The kicks accumulate. Over thousands to millions of years, they alter the asteroid's orbit, increasing its eccentricity until it crosses the orbit of Mars, or Earth, or falls into the Sun. The Kirkwood gaps are regions where Jupiter has, over 4.5 billion years, systematically cleared the asteroid belt of objects. Not by direct collision, Jupiter has never physically swept through the asteroid belt. By gravitational perturbation, by repeatedly kicking objects out of resonant orbits until they went somewhere else. Some of those objects went somewhere else in the direction of Earth. The asteroid belt is the source of the majority of near-Earth objects, the asteroids and meteoroids that cross Earth's orbit and represent the ongoing impact threat to our planet. Jupiter's gravitational perturbations are the primary mechanism by which objects from the main belt are placed into Earth-crossing orbits. Jupiter creates the threat it partially mitigates. Let's start with the protective role, the role that is more commonly discussed and more emotionally satisfying. The hypothesis that Jupiter acts as a shield for the inner solar system was first formalized by George Wetherill in 1994 in a paper published in Astrophysical Journal Letters. Wetherill used computer simulations to model the solar system both with and without Jupiter, and found that without Jupiter, Earth would be struck by long-period comets approximately 1,000 times more frequently. 1,000 times more frequently. The current rate of large comet impacts on Earth is already sufficient to have caused multiple mass extinctions in Earth's history. 1,000 times that rate would mean a major cometary impact on Earth approximately every few million years, rather than every few billion years. An impact frequency that would likely prevent the sustained development of complex life. Wetherill's result was striking, and it has been refined by subsequent simulations. The current consensus is more nuanced than a simple 1,000-fold reduction. The protective effect of Jupiter depends strongly on the type of impactor, the time period, and the specific orbital configuration. But the broad conclusion that Jupiter significantly reduces the rate of large impactor delivery to the inner solar system is supported by the available evidence. The mechanism of Jupiter's protection is gravitational ejection. Objects entering the inner solar system on trajectories that bring them close to Jupiter are subject to gravitational assists. Their trajectories are bent by Jupiter's gravity in ways that can dramatically alter their orbits. Many of these objects are ejected entirely from the solar system, given enough energy by the Jupiter flyby to escape the Sun's gravity entirely. Others are placed in highly elliptical orbits that keep them in the outer solar system. Only a fraction are directed toward the inner solar system. Shoemaker-Levy 9 is the most dramatic modern demonstration of what Jupiter does to objects that come too close. In March 1993, astronomers Carolyn and Eugene Shoemaker and David Levy discovered a comet that had been captured by Jupiter's gravity and torn apart by tidal forces into 21 distinct fragments. The fragments were strung out in a line, a chain of cometary pieces, each ranging from a few hundred meters to approximately 2 kilometers in diameter, all following the same orbit around Jupiter. In July 1994, all 21 fragments impacted Jupiter in sequence over a period of 6 days. The impacts were the most energetically significant extraterrestrial events observed in the solar system during the 20th century. The largest fragment, designated G, produced an impact scar in Jupiter's atmosphere larger than Earth's diameter. The total energy released by all 21 impacts was estimated at approximately 300 times the world's total nuclear arsenal. Astronomers and planetary scientists watched it happen in real time. It was the first time in history that humans had directly observed the collision of two solar system bodies. If Shoemaker-Levy 9 had not been captured by Jupiter's gravity, if it had continued on its original trajectory, where would it have gone? The answer depends on the specific orbital parameters, which cannot be reconstructed with certainty. But the broader point is not about this specific comet. It is about the category. Jupiter captures, disrupts, and absorbs objects that enter its gravitational influence. Some of those objects would otherwise have continued into the inner solar system. You did not see Shoemaker-Levy 9 impact Earth in 1994. Jupiter did. The Shoemaker-Levy 9 impacts of July 1994 were observed by virtually every major telescope on Earth and by the Hubble Space Telescope, which had recently been repaired by the first Hubble Space Telescope servicing mission in December 1993. The impacts occurred on the night side of Jupiter, but were rotated into view within minutes. The impact scars, dark patches of disrupted atmosphere, were visible for weeks after the impacts. The event provided the first direct confirmation of the theory that Jupiter absorbs objects that would otherwise threaten the inner solar system. But the protective role of Jupiter is not as straightforward as Weatherill's 1994 paper suggested. Later simulations, more sophisticated, with better orbital data, have complicated the picture significantly. A 2008 paper by Kevin Grazier and colleagues, published in the journal Astrobiology, modeled the delivery of material to the inner solar system both with and without Jupiter, and found results that challenged the simple shield hypothesis. Their simulations showed that in some configurations, Jupiter actually increased the delivery of material to the inner solar system, not by deflecting objects inward, but by destabilizing the outer solar system in ways that sent more material toward Earth than would have arrived in Jupiter's absence. A 2010 paper by Jonathan Horner and Barry Jones reached similar conclusions. Their simulations found that the protective effect of Jupiter depended sensitively on Jupiter's exact mass and orbital parameters, and that for some configurations, a less massive Jupiter or a Jupiter in a different orbit actually resulted in fewer large impacts on Earth, not more. The simple story, Jupiter shields Earth, therefore Jupiter is our protector, turns out to be a significant oversimplification. Jupiter does deflect many objects that would otherwise threaten Earth. It also perturbs objects into Earth-threatening orbits that would not be there in its absence. The net effect, whether Jupiter's presence makes Earth safer or more dangerous, depends on the specific population of impactors being considered, the time period being modeled, and the parameters of Jupiter's orbit. The real Jupiter, in the real solar system, does both, simultaneously, continuously. Now let's talk about the other side of Jupiter's gravitational influence, the side that is less commonly discussed and more genuinely alarming. Long-period comets are objects with orbital periods exceeding 200 years, objects that spend most of their time in the outer solar system, in the Oort cloud or the Kuiper belt, and only occasionally enter the inner solar system. They are different from the asteroids of the main belt. They come from further away. They carry more ice, more volatile material, more uncertainty. Long-period comets are not perturbed by Jupiter into inner solar system orbits. They are sent there by perturbations from passing stars, giant molecular clouds, and the galactic tide. They arrive in the inner solar system on highly elliptical orbits, moving at high velocities with essentially no warning. And when they enter the inner solar system, Jupiter's gravity is the dominant force acting on them. For short-period comets, comets with orbital periods less than 200 years, Jupiter is directly responsible. These objects have been captured from the outer solar system by Jupiter's gravity over millions of years, their orbits progressively modified by repeated Jupiter flybys until they are in the inner solar system with periods of years to decades. The family of short-period comets most strongly influenced by Jupiter is called the Jupiter family comets. The Jupiter family comets are a direct product of Jupiter's gravitational influence. They would not be in the inner solar system without Jupiter, and they cross Earth's orbit. Comet 67P/Churyumov-Gerasimenko, the target of the European Space Agency's Rosetta mission, which placed a lander on a comet for the first time in 2014, is a Jupiter family comet. Its current orbit brings it within the inner solar system every 6.4 years. Its orbit intersects a region of space that Earth also passes through. The probability of a collision between 67P and Earth in any given orbit is extremely small. But it is not zero. and 67P is one of thousands of Jupiter family comets in the inner solar system. Now consider the question of where long-period comets go when Jupiter's gravity acts on them. A long-period comet entering the inner solar system has a significant probability of passing close to Jupiter. If it does, one of three things can happen. Jupiter can eject it from the solar system entirely. This is the most common outcome. Jupiter can capture it into a shorter period orbit. This is how Jupiter family comets form. Or Jupiter can deflect it onto a trajectory that is more likely to intersect the inner planets. That third outcome, deflection toward the inner solar system rather than ejection from it, is not the most probable outcome of a Jupiter encounter, but it is a real outcome. And for some fraction of long-period comets entering the solar system, Jupiter's gravity is the mechanism that puts them on a collision course with Earth. The Chicxulub impactor, the object that ended the Cretaceous period 66 million years ago and killed the non-avian dinosaurs, has been the subject of ongoing debate about its origin. Was it an asteroid from the main belt, perturbed into an Earth-crossing orbit by a Kirkwood gap resonance with Jupiter? Or was it a long-period comet sent into the inner solar system by a distant perturbation and then focused toward Earth by Jupiter's gravity? A 2021 paper by Siraj and Loeb in Scientific Reports proposed a specific mechanism, that the Chicxulub impactor was a fragment of a long-period comet that passed close to Jupiter, was tidally disrupted by Jupiter's gravity into multiple pieces, and had one of those pieces deflected toward Earth. The paper used statistical arguments about the composition of the Chicxulub impactor and the frequency of such events to argue that this mechanism could account for the observed impact rate of Chicxulub-class objects. The paper is contested. The hypothesis has not been confirmed, but it represents a specific, physically motivated scenario in which Jupiter is not the shield that protected Earth from the Chicxulub impactor. Jupiter is the mechanism that delivered it. The origin of the Chicxulub impactor has been studied using both the geochemical signature of the impact layer, the KPG boundary, and dynamical models of impactor delivery. The impactor left a signature enriched in iridium and other siderophile elements, consistent with either a carbonaceous chondrite asteroid or a cometary impactor. The crater's diameter of approximately 150 kilometers implies an impactor of approximately 10 to 15 kilometers, with a kinetic energy equivalent to approximately 100 teratons of TNT. The Siraj and Loeb 2021 paper used the observed frequency of long-period comets and Jupiter's tidal disruption cross-section to argue that the long-period comet hypothesis could explain the observed frequency of Chicxulub-class events. Think about what this means for the narrative of Jupiter as Earth's protector. The most devastating impact event in the last 66 million years. The event that ended the dinosaurs, that reset the evolutionary trajectory of vertebrate life on Earth, that created the conditions for the eventual dominance of mammals and ultimately the emergence of your lineage, may have been caused, at least in part, by Jupiter's gravity. Not Jupiter as a passive redirector of an already dangerous object. Jupiter as the active mechanism that took a long-period comet that might have remained harmlessly in the outer solar system for millions of years, tidally disrupted it, and put a piece of it on a collision course with Earth. The planet that is responsible for your existence may be responsible for the near extinction of your ancestors' ancestors. Protector and threat. The same gravitational field. The same physical mechanism. Different geometry. Stop here. The same gravitational mechanism, Jupiter's tidal forces, that tore Shoemaker-Levy 9 apart before it could reach Earth, may have torn apart the comet that eventually killed the dinosaurs and put one of its pieces on a trajectory toward Earth. Jupiter saved us from one comet and may have delivered another. If you had to choose, a solar system without Jupiter, accepting higher baseline impact rates but no Jupiter-focused delivery, or the solar system we have, which gives Earth better long-term survival odds? Drop your answer below. Planetary scientists genuinely disagree on this. Now let's talk about the most disturbing thing Jupiter has ever done. Not an impact event, not a comet deflection. A period in the early solar system when Jupiter's orbit migrated so dramatically that it nearly destroyed everything that would eventually become the inner solar system. It is called the Grand Tack. In the early solar system, in the first few million years after the formation of the Sun, the planets were not in their current orbits. The gas giants formed in a disk of gas and dust, and as they formed, they interacted with that disk gravitationally. These interactions caused the planets to migrate, to move through the disk to different orbital positions. The Grand Tack hypothesis, proposed by Kevin Walsh and colleagues in a 2011 Nature paper, describes the following sequence of events. Jupiter formed first, at a distance of approximately 3 to 4 astronomical units from the Sun, roughly where the asteroid belt is today. As it formed, it opened a gap in the disk and began migrating inward, toward the Sun. This inward migration was driven by the interaction between Jupiter's gravity and the disk material. Material inside Jupiter's orbit pushed it outward slightly, while material outside pushed it inward more strongly, causing net inward movement. Jupiter migrated inward to approximately 1.5 astronomical units, roughly where Mars is today. During this migration, Jupiter swept through the region of the inner solar system. Objects in its path were either captured into resonant orbits, scattered outward, or ejected from the solar system entirely. The Proto-Earth and Proto-Venus existed during this period, in embryonic form, as larger-than-average planetesimals, and survived the Jupiter migration only because they were in the right orbital positions to avoid catastrophic disruption. Mars would have been much larger than it is today. The Grand Tack hypothesis explains Mars's anomalously small mass as a consequence of Jupiter sweeping through the region where Mars was forming, depriving it of the material it needed to grow to Earth-like size. Then Saturn formed, and when Saturn reached a specific mass, approximately 60 Earth masses, it entered a 2 to 3 orbital resonance with Jupiter. The resonance changed the dynamics entirely. Instead of continuing to migrate inward, Jupiter began migrating outward, tacking in the sailing sense, reversing direction. Saturn followed, also migrating outward. Jupiter and Saturn migrated outward together until the disk dissipated, leaving them in roughly their current orbital positions. The Grand Tack hypothesis explains several features of the solar system that are otherwise difficult to account for. Mars's small mass, the structure of the asteroid belt, the composition of the inner solar system planets. It is not universally accepted. It is a model, and like all models, it makes predictions that can be tested against observations. But if the Grand Tack occurred, then Jupiter did not merely shape the solar system from its current position. It physically invaded the inner solar system, swept through the region where the terrestrial planets were forming, removed most of the material that would have gone into making a larger Mars, and then retreated to its current orbit. The inner solar system as it exists today, Earth, Venus, Mars, the asteroid belt, is the product of Jupiter's migration. Jupiter did not protect the inner solar system during its formation. It restructured it. The Grand Tack hypothesis was published by Walsh, Morbidelli, Raymond, O'Brien, and Mandel in Nature in 2011. The name references the sailing maneuver in which a boat changes direction by turning through the wind. The hypothesis explains the mass deficit of Mars, which is approximately 10 times less massive than Earth, despite forming in a region of the disk that should have supplied sufficient material for a larger planet, as a consequence of Jupiter's inward migration depleting the Mars-forming region before Mars could grow. Subsequent simulations by the NICE model group have incorporated the Grand Tack as an early phase in the dynamical evolution of the outer solar system. Now we come to the simulation result from 2009 that I mentioned in the introduction. In 2009, Jacques Lascar and Michel Gastineau at the Paris Observatory published a paper in Nature presenting the results of 2,501 numerical simulations of the solar system's long-term orbital dynamics. Each simulation ran the solar system forward by 5 billion years, the approximate time remaining before the sun becomes a red giant. The simulations were not identical. They varied the initial conditions by extremely small amounts, changes in Mercury's position by as little as 1 meter, to explore the range of possible future orbital evolutions. In approximately 1% of the simulations, 25 out of 2,501, Mercury's orbit became unstable. Mercury is the smallest and innermost planet. Its orbit is already the most eccentric of the 8 planets. It varies significantly in its distance from the Sun over the course of its year. Under the right conditions, gravitational perturbations from Jupiter, specifically an orbital resonance between Jupiter's precession and Mercury's orbital precession, can drive Mercury's eccentricity to extreme values. In Lascar and Gastineau's simulations, when Mercury's eccentricity increased sufficiently, one of several outcomes occurred. Mercury could fall into the Sun. Mercury could be ejected from the solar system, or, in a smaller fraction of cases, Mercury's orbit could intersect the orbit of Venus or Earth, leading to a direct collision. A collision between Mercury and Earth. The combined mass of Mercury, approximately 5.5% of Earth's mass, impacting Earth at the relative velocities involved, would be a catastrophic event, not a mass extinction. A planetary-scale catastrophe, an impact that would strip Earth's atmosphere, vaporize the oceans, and render the planet uninhabitable for geological timescales. In some of Lascar and Gastineau's simulations, the destabilization of Mercury's orbit propagated. Mars was ejected from the solar system. Venus and Earth experienced close approaches. The entire inner solar system entered a chaotic regime from which the terrestrial planet system could not recover. And Jupiter's gravity is the mechanism. The orbital resonance that drives Mercury's eccentricity is a resonance with Jupiter's orbital precession. Jupiter is not directly sending Mercury toward Earth, but Jupiter's gravitational influence on the precession of the solar system's orbital dynamics is the mechanism by which Mercury's orbit can become unstable. 1%. In 1% of simulations, the inner solar system destroys itself from the inside within the next 5 billion years. This does not mean there is a 1% chance of this happening. The simulations varied initial conditions by amounts that correspond to quantum-level uncertainties in planetary positions, changes that the inherent uncertainty of quantum mechanics makes fundamentally unknowable. The 1% figure is not a probability of a specific future. It is a measure of the solar system's sensitivity to initial conditions, of how chaotic the long-term orbital dynamics are. What it tells you is that the solar system is not deterministically stable. It is chaotically stable. Stable in the sense that catastrophic orbital instability is unlikely in any given time period, but not stable in the sense that it is guaranteed to remain in its current configuration indefinitely. Jupiter made the solar system what it is. Jupiter is also the reason it might not stay that way. Lascar and Gastineau's 2009 Nature paper, Existence of Collisional Trajectories of Mercury, Mars, and Venus with the Earth, used a symplectic integrator specifically designed for long-term planetary orbit simulations, incorporating general relativistic corrections to Mercury's perihelion precession. The paper identified the G1 equals G5 secular resonance between Mercury's perihelion precession frequency and Jupiter's as the primary mechanism for Mercury orbit destabilization. The result confirmed and extended earlier work by Lascar, 1989-1994, showing that the inner solar system is chaotically unstable on timescales of tens of millions of years. Let's zoom out from the specific history and dynamics of our solar system and ask a broader question. Is Jupiter unusual? Do other planetary systems have gas giants in similar positions? And if they do not, what does that say about the prevalence of complex life in the universe? The question of whether Jupiter-like planets are common or rare in other planetary systems has been one of the central questions in exoplanet science since the first exoplanets were discovered in the 1990s. The initial picture from exoplanet surveys was discouraging for the Jupiter as life enabler hypothesis. The first gas giants discovered around other stars were not Jupiter analogs. They were hot Jupiters, gas giants in extremely close orbits around their host stars, with orbital periods of days rather than years. Hot Jupiters are not where Jupiter is. They are far closer to their host stars than Mercury is to the Sun. Hot Jupiters pose a significant problem for inner solar system stability. A gas giant in a close orbit around a star would disrupt the orbits of any terrestrial planets that had formed in the inner system. Either the hot Jupiter migrated to its current position from further out, sweeping through and disrupting the inner system as it migrated, similar to but more extreme than the Grand Tack, or the inner system never formed stable terrestrial planets in the first place. A planetary system with a hot Jupiter is almost certainly not a planetary system with an Earth-like planet in a stable, habitable zone orbit. The prevalence of hot Jupiters was initially estimated at approximately 1% of solar-type stars. More recent surveys, particularly from the Kepler Space Telescope, have refined this to approximately 0.5 to 1%. Hot Jupiters are present, but not dominant. What about cold Jupiters? Gas giants in Jupiter-like orbits far from their host stars. These are harder to detect with the transit method used by Kepler because they transit their host stars infrequently, and the transit probability decreases with orbital distance. But radio velocity surveys, which measure the wobble induced in a star by an orbiting planet, can detect cold Jupiters more effectively. Current estimates suggest that approximately 10% of solar-type stars host a cold Jupiter, a gas giant in an orbit beyond approximately 1 astronomical unit. This is a rough figure with significant uncertainties, but it suggests that Jupiter analogs, while not universal, are a meaningful fraction of solar-type star systems. The question of whether a cold Jupiter is beneficial or harmful for inner solar system habitability, whether it acts as a shield or a threat, or some combination of both, is the same question we have been discussing throughout this video. And the answer, as we have seen, depends on the specific configuration. A 2015 paper by Horner and colleagues modeled a range of Jupiter analog configurations and found that the effect of a Jupiter-like planet on inner solar system impact rates was strongly dependent on Jupiter's mass and orbital eccentricity. Low eccentricity Jupiters in circular orbits provided moderate protection with limited threat amplification. High eccentricity Jupiters provided less protection and more threat. Our Jupiter has a relatively low orbital eccentricity, approximately 0.049. It is nearly circular. This configuration may be near optimal for the balance between protection and threat that has characterized Jupiter's role in Earth's history. We may have gotten lucky, not just in having a Jupiter, but in having a Jupiter with the right mass, in the right orbit, with the right eccentricity. Or the solar system that produced Jupiter with these properties may be more common than we currently estimate. The data from current exoplanet surveys is incomplete. We have a strong detection bias toward large planets in close orbits. The population of cold Jupiters in circular orbits around solar-type stars is not yet well characterized. What we can say is this: the solar system you live in is not obviously typical. Jupiter's position, mass, and orbital properties, and the role they play in shaping Earth's impact history and orbital stability, represent a configuration that may not be universal among planetary systems. You exist because of a planet you have never visited. Jupiter formed first. It migrated inward through the inner solar system, restructuring the material that would eventually become Earth, Venus, and Mars. It retreated to its current orbit when Saturn formed and entered resonance with it. It has spent the past 4.5 billion years deflecting some impactors away from Earth and redirecting others toward it. It may have been part of the mechanism that delivered the Chicxulub impactor that ended the non-avian dinosaurs. And its gravitational influence on the long-term orbital dynamics of the inner solar system means that in approximately 1% of possible futures that are indistinguishable from our actual future given the inherent uncertainty of chaotic dynamics, Mercury's orbit destabilizes and the inner solar system enters a catastrophic reorganization. Protector and threat, creator and destroyer, the planet without which the chain of events that produced you would almost certainly have been different enough to not produce you, and the planet that has repeatedly threatened, and in some cases may have caused, the extinction of the life it helped make possible. This is not a contradiction. It is a description of how gravity works at the scale of a solar system. A single gravitational field, operating through the same physical laws in every interaction, producing outcomes that range from the deflection of a civilization-ending impactor to the delivery of another one. Jupiter does not choose. It does not protect or threaten. It simply is. 318 Earth masses of hydrogen and helium in an orbit that has been reshaping everything around it for 4.5 billion years. You are one of the things it shaped. One question. If you could redesign the solar system, same sun, same total planetary mass, same distance distribution, but you could choose Jupiter's mass and orbital position, what would you change to maximize the long-term survival of complex life on Earth? Make Jupiter bigger? Smaller? Move it further out? Change its orbital eccentricity? Drop your specific proposal below. I will model the most interesting ones against the Laskar-Gastineau stability results in the next video. Next video. What happens when two neutron stars collide, if the collision happens close enough to matter? The event we detected in 2017 that shook space-time produced more gold than exists in the entire Earth and what a nearby version of it would do to us. See you there.